4, 5, and 6 from the Unit 2, Lesson 5, Solving Inequalities. So I'm going to put lines going straight down. You may have remembered doing this when you were in middle school or 9th grade. And I want to isolate x in the middle. So I start by adding or subtracting. In this case, I'm going to subtract 12 from all three columns, -4. Remember, adding or subtracting does not change the direction of the inequality symbol, but now I divide by -3. And since I am dividing by a negative, now I will flip. So two negatives flip to give you a positive 4/3. And this flips as well to give us a negative 5/3. So I'm making my number line. Sometimes students think like, well, which one goes to the left? Well, a negative is always smaller than a positive. So this is negative 5/3. This is positive 4/3. I'm going to put an open circle at 4/3 and a closed dot at negative 5/3. So this point is included in the solution set of the mathematical statement. Now, how do I know where to shade? So let's go back to what is pointing towards the x. Notice that for this particular value, I have this symbol facing towards it. So x's, or the values representing the solution set, have to be less than this value. Less than is to the left. Also, it says that x's have to be greater than or equal to this value, or greater than is to the right. So I'm going to go ahead and shade in between. Okay, looking at number 5. So number 5, when we have absolute value, remember absolute value means the distance from a particular value. So if you say the absolute value of 2, there's two places on the number line that have a distance of 2, both -2 and +2. And so for that reason, because distance is always measured as a positive value, I'm going to take this statement and I'm going to turn it into something like this. So -2 goes on the opposite side. I keep the symbol going in the same direction, bringing down x plus 4 and what I already have. Okay, now I can only do this when this value, by the way, is when this value is a positive. So in this case, I'm going to subtract 4 from all three columns. Now I've isolated the x, and let's talk about what this means. So if I make a number line up here, -6 and -2, -6 is smaller than -2. This says, okay, so I've flipped my symbols, just making sure. Let's see here. I did not need to flip my symbols. I thought for a second I divided there when I quickly looked down. So this says that x's have to be greater than -2. So greater than -2 would be to the right. And this says the solution set has to be less than -6 or less than -6. So what this says is that if we were going to identify the numerical values that I could plug into this mathematical statement and it would be true, it'd be any value to the left of -6 or to the right of -2. Like 0 would work, for instance. 0 plus 4 is 4, the absolute value of 4 is 4, and yes, 4 is greater than 2. Or I could choose something like -10 down here, because that's in the shaded region. -10 plus 4 is -6. The absolute value of -6 is 6, and yes, 6 is greater than 2. Okay, let's do the exact same thing with number 6. So same concept, I'm taking -17, keeping the symbols the exact same, 5 plus 2x, and I'm bringing down my lines, subtracting 5 from all three columns, and what do I end up here with? -22, 2x, and subtracting 5 here to get 12. Now I did not divide by a negative, so I am not switching any symbol or the direction of any symbol. And then I'm going to make a little number line up here. I have -11, I include that point. I have +6, I include that point. And what does this say? It says the solution set is going to be less than 6, okay, less than 6, and it has to be greater than or equal to -11. So it's in between that I'm shading. Let's look at 7, 8, and 9 next.